Hey, welcome back. Today we're going to be talking through another AP Physics C Mechanics FRQ. This is from 2023. It's number 2, set 2, so it's the second set, and it's on primarily simple harmonic motion and forces. Now, this is a good thing to practice because it's almost always a good idea to practice FRQs in preparation for the AP Physics C Mechanics test, but there are also some interesting things that come up during this FRQ, so it's definitely worth doing. Alright, let's go ahead and get to it. I'm going to try to avoid reading at you as much as possible. If you want to pause this and read this to yourself, go for it. I'm just going to point out a couple major things that are happening here. So you've got a mass on the left-hand side, and it's being supported by a student. And the way it's being supported, there is no compression on the spring, no compression or tension on the spring. So in a way, you could just say, well, it's got a force due to gravity going down and the normal force from the hand. So you could call it the force from the hand or the normal force or the applied force, and that's what's going on here. But it hasn't been released. If it was released, it would be stretched down like some distance down below here, until you had a restoring force that would be greater, so that would be the force of the spring, or Hooke's law going backwards, which would be greater at that point than the force due to gravity, which would cause it to accelerate back upwards, and then that motion would repeat in a simple harmonic fashion. So that's the premise of what the problem is talking about. We've got a repeating motion that's going to happen once the hand releases the system. There's a motion detector detecting what's going on, and in the second case, notice that there are two springs hooked up. Now, when you have two springs hooked up, essentially in parallel, we would say, that would double the spring constant. You add the spring constants together for the springs that are hooked up in parallel, and assuming these are the same springs, then that would just add two of identical K values together, or essentially double the original value, you could say. So that's the background for what's going on. A starts out by asking us to derive an expression for T, which is the period, as a function of N, which would be the number of springs that would be added to the system. Express your answer in terms of M, K, N, and physical constants as appropriate. Alright, well, this is a mass spring system, right? And on your equation sheet is an equation for the period of a mass spring system. There's also the period of a pendulum on your equation sheet as well, but we are definitely focused on the period of a mass spring system. So I just went ahead and put it up there, and it's asking us to think about what's going on here. So we could say, well, our spring constant, our equivalent spring constant, is going to be equal to N, which is the number of springs that we have in parallel, times K. Or you could just say K equivalent is equal to the sum of the K values for all of the springs that are added up in parallel with each other, so to speak. So let's go with this definition here for now. Each spring is going to be identical. So we're going to take this equation and just modify it and make our K into like our K equivalent. So how would we do that? We would say it's 2 pi times the root of m over nk. So that's going to be your answer for this early intro part of the problem here. We're going to build on that, of course, as we almost always do for AP Physics C Mechanics problems. Okay, and so B says on the following axes sketch a graph of T, period, as a function of n, the number of springs that we have in parallel for the system, for n is greater than 1. Alright, so let's think about what would happen. If we had a setup where we had T is proportional to 1 over the root of n, that would give us a positive linear system like this. We would expect to see something like that. That's not what we have. We've got T with n over here. So if we had something like that, we would actually have a system that would look something like this. And let's think about why this is. We're talking about n values of greater than 2 or something. So let's think about what would happen here. If we had this would be 2, this would be 10 or something. We can plug in some numbers and test it out. So the period where n equals 2, and we just pick standard units. Because we're going to do a relative comparison problem, we can forget about anything that's constant here. It's really important to mention that the spring is supposed to be ideal, which would mean it would be massless. So we can ignore the mass of the springs in theory as we do this comparison. The 2 pi we can ignore. The only thing that we're really varying is going to be the n. So if we say the square roots of 1 over 2, something like that. Let's think about what the square root of 1 over 2, and we'll make this proportional and approximate here. Just for clarification purposes, that would be 0.7. Well, what would be the period for n equals 10? Just to not get an idea, we would say that it would be proportional to 1 over 10. Well, that is going to be 0.3. So you're already getting the idea that it does go down, similar to what we were talking about. Let's do something in the middle. Let's say t for n equals 5 and try to anticipate what the relative comparison problem would be. If we do the root of 1 over 5, that would be equal to 0.45. So if I did a better job of plotting this, you could see that you would end up with something like this. I'm not the greatest artist with my tablet, but it would be something along these lines, where you would get a concave up relationship right here, and it would be giving us an indication the graph should look something like this. Alright, so that's how you would go about approaching B. Let's think about how to approach C. Okay, and so for part C, it says the student plots the data for t squared, period squared as a function of n to the -1 power. Let me just remind everyone, 1 over n is equal to n to the -1 power, right? So just a quick reminder there. So that's actually the type of relationship that we need, because if you look at what we have for this relationship, if we squared everything, then you would have the period squared is equal to 4 pi squared times m over n times k. If you think about that, on the y-axis you could have t squared, and on the x-axis you could have 1 over n, and that would give you a linear relationship. And that's why we have a linear relationship here with this data. That's what we would expect. So first of all, they ask us to draw the best fit line for the data. So let's take our straight edge and do that. Now it's a little bit easier if you're on the test to do that. I do want to mention a couple things as a reminder when you draw a line of best fit. You're going to draw a line that is going to split the difference, so to speak, between the point values on one side of the line and the same number of points on the other side of the line, so to speak. So it looks something like this in this case. And in this case, the data does go basically straight through the origin. However, don't make it go through the origin. Oftentimes there are problems that are clearly offset, there's some y-intercept value, and you have to come up with some explanation as to why that is. In other words, don't make that line fit through the origin just because conceptually it should go through the origin. Next up, what I'm going to do is look for 2 points that are easy to read on my graph to be able to calculate the slope. This one looks pretty solid, as well as this one over here. We're going to have this as our initial, this is our final point. Let's put in some coordinate points here to get this. Okay, and then immediately when I'm doing these problems, I start thinking about taking the slope. You're going to need the slope, and it's going to be helpful. I can't think of a time when you would not calculate the slope in any of these problems that I've seen, so I would just say get used to immediately starting to solve for the slope, and we'll think about what that means. We'll apply it in a moment. Okay, and so if you do the calculations here, you end up with 12 seconds squared are our units, because the number of springs doesn't really have a unit associated with it, so it's just this second squared business, and there are no units here. And I just ran out of room, but that's 12 seconds squared. Next, for C2, it says the mass of the block is measured to be 1.5 kilograms. Using the graph, calculate an experimental value for the spring constant K for a single spring. Alright. So the next thing we're going to do is think about what the slope is. We can actually just start to pull this out. We can say this TS, the period of a spring squared, that is effectively, that's going to be like our Y value over here, right? And we still have 4 pi squared, and we want to pull out the n value. So here is m over k, and we want to have times n. If we do that, then you could say this effectively becomes our x, and this in here becomes our m. We have no b, so we're setting this up as a linear format, the equation of a line, y equals mx plus b. That's what we're doing here, and if we do that, then this value I've labeled as a red m becomes our slope. That's really crucial. Let's go ahead and write this down. So I'm going to say the slope is equal to 4 pi squared times m over k, where m is mass and k is the spring constant. That's really crucial. And I'm just going to copy and paste that on the right side to have some more room with this. I can say that in this problem, we know what the slope is. We can plug this value in, and we want to solve for k, right? So to be able to isolate for k, we could say k is equal to 4 pi squared times m over the slope. So notice I've just algebraically changed positions of k and the slope with each other, and now I've isolated for k. So let's go ahead and write that information over here. We have 4 pi, and I need to make sure that that is squared. And if you do the math, it turns out to be 4.9. That's going to be in newtons per meters, which is the typical units that we have for a spring constant. I suppose you could say 4.93 if you wanted to take that to 3 sig figs. And that's how you go about solving this. So this is a really, really crucial skill to be able to set up an equation where you're figuring out what the y equals mx plus b components are of an equation in terms of other variables, solve for your unknown, given the experimental slope that you're going to almost certainly need to calculate on a graph, and solve for one of the parts, connect that to the slope. So we're done with C2, and so let's move on to C3. The student finds that the value given by the manufacturer for the spring constant is larger than the value determined experimentally in part C2. Determine a single source of experimental error that could result in the observed difference in the value for k. Briefly justify your answer. Okay, fair enough. So if k is larger, let's go back to here. I'll put this in yellow so we can focus on the k right here so you know what I'm looking at and thinking about. So we're going to focus on the k, and let's think about it. There are a number of things that we could say. Notice the only variable that we have directly for this version of k is just the mass. So you could say something like, okay, the experimental value for the mass was too small. If the mass was too small on the experimental side of things, then we could say like k would be smaller than it actually is, you could say. So that's an easy way of addressing this. If you want to work with other variables, you can, but that's the way I would do it. So an easy way of justifying that is to say something like the mass of the block was measured, but the mass of the spring attached to it is some non-zero value, so the mass of the block was measured to be too small. Something along these lines here, and that's how you would approach C3. Let's go ahead and move on and see what D has in store for us. Okay, and so for part D, what's happened is the system has been switched to be a horizontal system, and the experiment is more or less repeated. And the question, you can read it here and pause if you like, but essentially the question is, the student again plots t squared as a function of n to the -1 power for this new data. Would the slope of the best fit line from this new investigation be greater than, less than, or the same as the slope of the best fit line in part 1? So let's think about what's changed. In this scenario, what has changed is it's just essentially horizontal now as opposed to vertical. And what that would do is, in this case, you wouldn't have gravity unopposed like you would in a vertical system. Here you would have the normal force that would counteract the gravitational force, but that is irrelevant. So if you look at what determines the period of a pendulum over there, we have already written this out with a system with multiple springs. You just throw on an n into the equivalent k value for the spring constant. So notice that you have an m there, you have an n, and you have a k. You don't have gravity in there, so the answer is it's going to be the same as before. And so how do we justify this? We could say, okay, so we could say something like the period. You write this in a way that can be read. By the way, you should try to preview what you're writing and practice what you're writing in such a way that your grader can read your writing. If your grader cannot read your writing, you won't get credit, so just be careful with that. But it says the period of a mass spring simple harmonic motion system depends on the root of the mass and the spring constant, not the gravitational force. So changing the orientation of the system would not change the period. Okay, and so for part 2, let's think about what this is saying. The maximum speed of the block is found to be Vmax. When n increases, will Vmax increase, decrease, or stay the same? Well, what's going to happen is it's going to increase. Let's think about why that is. If you were to increase the n, the value, the number of springs, and pull back if you were to pull back the same amount, that would increase the potential energy as the object is displaced from equilibrium. Now you've got more springs restoring the object back to its equilibrium position, so it's harder to do, so it's got more stored potential energy with more springs. If that's the case, it also has more kinetic energy as it goes through, as it oscillates back and forth through equilibrium. So the kinetic energy would increase as well in the process. So I would take the time to translate that into a sentence or two, but that's kind of the shorthand version of how to answer D2. In any case, I hope that's been helpful. I have done lessons on an entire year of physics, as well as most of the ideas in AP Physics C Mechanics. If you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.